Okay, I want to pick up where we left off, talking a little bit about efficiency and linear algebra. We're going to talk a lot more about linear algebra when we actually get to the unit on numerical linear algebra, so a lot of these things will come up again, but I just wanted to mention a few of them here as we were talking about efficiency. Okay, so first thing I just want to show you an example of doing some matrix vector multiplication and just think through a little bit about some of the things that come up if we think about this computation. So I'm taking a matrix A, I'm multiplying it by another matrix B, and multiplying by a vector X. I'm using upper and lowercase to try and delineate matrices versus vectors. And if these are 5,000 by 5,000 matrices, if we time this in R, it takes either 15 seconds or 8 seconds, depending on our perspective on the problem. The elapsed time is the actual clock time that it took, and the user time is basically the time it took to do the computations. And the reason that we're seeing this disparity of essentially twice as much here is because this particular machine has 2 cores, and if you're using the basic linear algebra subroutines, if you're using what's called the BLAS and then you're using a threaded version of that, it will be able to do spread out the computations across 2 cores. So in that case, that's the reason for this being twice as fast in terms of clock time as it is in terms of the actual time it takes to do all of the computations collectively. Okay, so these are both modestly large matrices and a modestly large vector X that we're multiplying together here. If I'm looking at this computation, one of the things that I want to think about is what the order of operations is in terms of how R actually does the computation. So if we think about what we're doing here, of multiplying these 3 pieces together, which order does it make more sense to do this computation in? Should I do this multiplication first and then multiply by this? Or should I do this multiplication first and then multiply by that? So in terms of thinking about that question, let's suppose that each of the matrices is n by n, and let's suppose this is an n-long vector. How many multiplications do I have to do if I'm going to multiply this vector by that matrix? N squared? Okay, this times this is going to involve n different multiplications. I'm going to do n rows, so this computation is going to be n squared multiplications. We'll talk more in detail in the linear algebra unit about whether we count the additions and count the multiplications and things, and sort of details like that. But for the moment, let's just think of this as how many multiplications we have to do. What about if we're multiplying these 2 matrices together? N cubed? Because we're now doing what we just said, a vector times a matrix. If we think of the first column here, that's n squared right there. There's another n squared here, there's another n squared here, so if we have to do n of these columns. So now this is going to be n cubed. You can imagine if n is 5,000, n cubed versus n squared is a pretty big distinction, right? Okay, so in light of that, what if we multiply this times this and then do the result times that? We get n cubed calculations plus n squared calculations, right? If we do AB and then x, that's going to be n cubed plus n squared. What if we do it this first? That's going to give us a vector instead of a matrix, right? So if we do A, B, x, that's going to give us n squared. We're going to then have a vector that gets multiplied by this, so that's also going to be n squared. So that's going to be n squared plus n squared. So this is a pretty big difference in terms of which order we did it in. So we would want to see if we can either check to see how R does it or make sure that we control what order R does things in. So let's see if it actually makes a difference to explicitly tell R that this is how we want to do the grouping. Okay, so that's a pretty big difference, right? So that the sort of more theoretical calculation here plays out as a difference of 8 seconds versus 0.2 seconds here. So that's a very large difference. and even if you're not doing a lot of these calculations, 8 seconds versus under a second starts to become, if you're not wanting to do a lot of, sort of having to sit around for 10 seconds to do a calculation. You'll notice there's not much difference in terms of the threading anymore, because it's harder, and there's relative to the amount of calculation that's going on. You're having to deal more with sort of the overhead of dispatching the calculations to the two different cores, when you're just talking about multiplying a vector by a matrix rather than a matrix by a matrix. Okay, so any questions about that? So this is a good example. We're just sort of pausing and thinking a little bit about some fairly basic things, like what order you do the calculations in can make a pretty big difference. Similarly, I'm not going to say too much about this, but oftentimes we end up working with the diagonal of a matrix when we're doing various kinds of statistical or computational calculations. And so in R and in other languages, there's functionality for just working with the diagonal. So for example, if I had a matrix X and I just wanted to modify the diagonal, it's going to be a lot more efficient to use the diag function and just modify the diagonal than it would be to add the original matrix plus a diagonal matrix, because sort of like what we were talking about on Friday in terms of sparse matrices and multiplication, there's no sense in doing all the addition of the off-diagonal elements, because we know they're not going to change if we're adding a diagonal matrix to another matrix. So don't do that calculation if you don't do the calculations that you don't need to do. So that's sort of what we're seeing here. And similarly, if you are multiplying a diagonal matrix by a matrix, that would also involve a lot of wasted calculations if you did all of the calculations involving the off diagonals of that diagonal matrix. So these are examples here. You can look at them in your own time in terms of how in R I would multiply a diagonal matrix times a full matrix, or a full matrix times a diagonal matrix, where you'll notice here I'm using the direct multiplication operator. I'm not actually using matrix multiplication. So whenever you see these sorts of, whenever you're sort of writing code to do these calculations, or if you see somebody else's code and you're running their code, have it pop into hopefully it'll pop into your mind like, oh, okay, that's one of those things where it's easy to make things more efficient. Okay, any questions about that? Okay, so I want to say a little bit about basically looking for objects. So the idea here is to think a little bit about how would we structure data objects and how would we do lookups if we had a lot of things to look up. So the basic idea here is, the basic context I'm thinking of here is I have a bunch of labels, or maybe I'm thinking of them as names, or I might call these things keys. And I want to look up the values associated with these labels or names or keys. So I want to go from some label and then look up the associated value. So the question is, how would we go about doing that in an efficient way? And if we're just looking up a few things, it's not really going to matter, exactly how we go about doing the lookup. But if we're looking up thousands, hundreds of thousands, millions of different things, then it can matter how the underlying structure of the storage for this is and the actual form that we use to do the lookup. So I sort of gave a little example here of how this might come up in a statistical context. If you were doing an ANOVA type analysis, then we've got a lot of sort of grouping structure where data values are grouped into clusters, and we might need to sort of look up cluster information for a given data value, or for a given cluster we might need to go get all of the data values for that cluster and then do some operation, some sort of stratified or clustered operation. So we've seen in R, I think I'm going to switch over to the actual demo code so we can run this. We've seen in R that we can actually look up things just by name or by label. So here I've got some values, and I've stored the values in a vector, but where I've got labels associated with each of the elements of the vector. So I'm just doing a little toy example here where they're labeled A through J. And then I've got this vector select that contains the things that I want to subset out or look up. And so I can do something like this. This is a straightforward operation in R. I can do the selection by passing in a vector of labels, and then R is going to look up in this little, essentially what's a table of name value pairs. It's going to look up the things that I'm interested in and pull back the results. So we've seen that, I think, in terms of named vectors. We could do that in terms of name. We can pass in a name or a vector of names to a list. We can do the same if we've got a matrix with named columns or named rows. We can pull out the columns or the rows by name as well. So there's nothing that stops us from doing that. And if we did it that way, the code is pretty clear because of the fact that we sort of associate, just because we work with language a lot, that's sort of a natural thing for us to do. But if we start to have to look up many, many objects, or if we have a very long table, if we have many hundreds of thousands or millions of elements here, then having to look up elements might take a while. And you're sort of seeing this in a different context in the problem on the problem set in terms of pulling out rows of a data set of a file. So what I'm experimenting with here is just I've set up either a list with some names associated with the list, or a vector x with names associated with the vector. And what I'm going to do is I'm just going to pull out the 500,000th element of the list by its index value or by the associated name of the element in the vector. And I'm similarly going to do the same thing in terms of the list, either pulling out by index number of the list or pulling out by name of the list. And we're going to see if that matters in terms of time. So the reason I only did this with 10 replications, as you can see up here, is because one of these is actually quite a bit slower than the others. I'm not totally sure why looking up by name label in terms of the vector is that much slower than in terms of the list. But in any event, this is much slower than looking up by index value. If I look up by the name, and even in terms of the list, it's much slower to look up in terms of look up the 500,000 element by its name as opposed to by its actual index value. Okay, so that leads to a question of sort of what could explain the fact that it's much slower to be looking up by name than it is to look up by index value. So any thoughts about what are the ways that R might be going through and doing this lookup by name versus the lookup by index that would make it much slower?
When it tries to match the index, actually match that one by one. Well, the name. If you're looking for the index, you just go directly to that.
Okay, so if it knows, for example, suppose we have a vector of doubles, and we know if we have to go to the 500,000th element of it. If we know how long each double takes in memory, which is I think is it Yang or Yang?
Yeah.
Yang, okay. Which is essentially what Yang was saying. If we need to go to the 500,000th element, we can just jump 500,000 steps and go to that place in memory and just pull the value out. But if we're looking it up by name, we don't know how far along to go to look to just grab the element out. So one possibility is it just has to look at each of the individual names to see, are you the name that I'm looking for? It reminds me of are you my, whatever that children's book is where the animal's going along and looking for its mother and asking, are you my mother? So so it has to go along and check with the first one, are you the one I'm looking for? Yes or no? The second one, are you the one I'm looking for? Yes or no? The third one, are you the one I'm looking for? All of that checking takes a lot of time to do that. So if it did actually do that checking in that way, that is what I think computer scientists call a linear search. And the lookup is going to essentially, it's going to be a function of how far along you have to go and how many elements there are that's sort of the same thing, I guess. How many elements there are in this set of things in which you're looking. Suppose that we had some way of ordering these labels. Can you think of another way to look up the name of the label? Yeah.
Well, if labels are ordered, you do a binary search.
Okay, so can you describe what a binary search is?
You look halfway.
Okay.
And then it's less than the second half. You just iterate the process.
Okay, so you might be able to be more clever, sort of taking a computer science perspective about how you do the lookup, and maybe you can sort of have the size of things that you're looking up by having these labels be ordered. So that could help you in terms of their more clever algorithms in terms of doing the search. I believe that binary search would take order of log n, where n is the number of elements. So the linear search is basically just going to take order of n, the number of things, whereas the looking it up in that sort of fashion would be rather faster. There's another way to do this, which goes by this name, this title called hashing, which we came across a little bit when we were talking about Git. So the basic idea of hashing is we're going to try and take some, say, file or some object or set of R objects or some input that's in sort of a not particularly structured format. And we're going to try and take the input, or what we might call the data, and use a hash function to convert it to, trying to get my terminology right here, to basically to then create an index. So we're going to take, we can think of these also as being either sort of the keys or the names. These are the things that it's a little bit hard to work with in terms of looking up things quickly. And they might even be different lengths. You might have files that are different lengths. So with the git commits, when it was trying to associate a unique label associated with each of the commits, the input it was getting was basically differences between what you'd done on the previous commit and what you did on this and the changes you had made. Those changes were sort of not in any sort of regular form of an equal length for any given change. So you would need one of these hash functions that can take these sort of unstructured inputs and basically convert them into an index in some form. So what we saw with Git was we saw that we're not going to go into the details of how these functions work, but basically there was some underlying function that converted this set of changes, this commit, into a hexadecimal base 16 number associated with that. So the basic idea is if you have one of these, you can basically use this to convert very quickly, if this function runs quickly, to very quickly convert from either sort of less structured data or converting from some arbitrary key or name to an index, and then you can look up by index. So an example would be that if you converted to a base 16 value, and then you wanted to look up by index, then you can just make the indexing basically based on the length of the number of different base 16 values that you could get out as a result of doing this hash function, and that would then provide you with an index. And so once you have an index, as we just said, we know we can then go quickly and go to the place that the index indicates in our set of objects. One of the things that happens with these hash functions, and this I wasn't very clear about this when I talked about this in Unit 2, is you don't necessarily get a unique index for different inputs. So the basic thing that's going to result if we're looking up things by name, by passing the name or the key through one of these hash functions, is you end up with sort of objects stored in what are sometimes called buckets. So you might have different values that result from the hash function, and then we might have multiple different things stored in each of these buckets. So the idea is if I have a key or a name, I pass it through this, that tells me which of the buckets to go look in, and then once I know that I'm in a particular bucket, then I would just need to go through and look and check which of the ones was the one that I was looking for. But the idea is as long as there aren't too many of these in a given bucket, the fact that I'm able to quickly get the position in my set of buckets here then would allow me to go quickly look up, for example, the one that I'm looking for. So that's just sort of a high-level, fairly quick introduction to this idea. But if you hear about hashing and hash table lookup, this is basically what's going on under the hood. So I'll show you an example, sort of a black box example of that in R. Are there questions about this before I do that? Okay, so what I'm going to do is we're actually going to use an environment. So this is basically using, we've already seen environments in terms of an environment is used to store the objects that are associated with a function call. And here we can actually create our own environment. And the nice thing about environments is that environments, if you look up objects within an environment, R actually implements that as a hash table. So it goes through this process to go look up the objects. And you can sort of understand why R would do that, because looking up objects is something that R has to do a lot because it's an interpreted language. You pass it the name of an object and say, I want to do something with this object. It then needs to go find that object in memory, pull out the value associated with it, and then do some manipulation with it. So it's doing this lookup all the time. So it makes sense that it does it, that it's implemented a fast way to do that. So we can sort of exploit that if this were really important to us, if looking up objects by name were something that we needed to do a lot, but we wanted to be able to do it quickly. I'm going to take that list from the previous example, and I'm going to convert it to an environment that I'm going to call xenv. So that's going to take a little bit of time to actually do. But once it does that, I can then look up in environments in the same sort of syntax that I use to look up a list. Here I need to use quotes when I'm looking up the object labeled 500,000 in the environment because it's a number, and otherwise I wouldn't like that formatting. But this, if I had an object named A, I would do $$, and here I'm just putting the number in quotes because I'm trying to use the number as an actual character string as a label. Similarly, I could look it up by passing in the character string that's the name of the element in the environment like this. If we want to see what this thing looks like, well, I guess I don't want to do ls on this because it's going to print out a whole bunch of stuff. But I could maybe, this will probably be okay. Although actually that needs to list it all out and then subset, so that's actually going to take a little while. But if I do the benchmarking, hopefully that won't take too long. If I do this benchmarking of, again, looking up the 500,000 elements either by index value in my list, in my vector, or by looking up by name in my environment, I'm going to do it 10,000 times. I'm going to have to go look up. I'm going to go look up this 500,000th one. Okay, that was a mistake. Okay, so you can see that these are the names of the objects in that environment that I converted from my list, because my list was something that looked like this. And so when I convert it into an environment, I just end up with objects with each of these names in my environment. And now if I do the timing, I can see that, first of all, I did 10,000 lookups, and that only took about 70 milliseconds, so that's pretty quick. And there's not much difference between looking up by name within the environment versus looking up by index value within the vector or within the list. In fact, these are essentially comparable with this. That wasn't the case when I did it on my other machine, but these were not very much slower than these when I did it on my own on one of the SCF Linux machines. So you can see this lookup is really fast when we do it this way. So I think the take-home message here is oftentimes this won't matter. Just write your code for clarity. But sometimes if you really are looking up lots and lots of stuff, then this can matter, and there are ways there are ways to do it quickly in R. There are ways to do it quickly in other languages. Okay, questions or comments? All right. I think I'm going to skip over some of the rest of this section. There have been some efforts in the last couple of years to basically rework R under the hood of how the language is actually implemented and written and executed to deal with some of the sort of slow pieces of R. So one of the examples of this is when R evaluates things like this, it actually explicitly creates a vector 1, 2, 3, 4, 5 up to end, and then it works on that vector. But if you think about what executing this code involves, there's no actual need to first create that vector and then iterate over that vector. You could basically write C code that does this stuff without doing all of that. But because R is an interpreted language, and because when it was first developed, that is how it was first written, there are a number of things like this that are built into R where there's sort of fundamental stuff that's sort of fundamentally baked in that causes slowness. So one of these efforts is this thing called PQR, for Pretty Quick R, by this statistician / computer scientist who's at Toronto in Bradford Neal. I won't go through the details here, but just to sort of make you aware of that. And then there's also there have been some efforts in the last 5 or 8 years to basically provide the ability to basically compile R code to some degree. And basically this compiles, you can actually take a function or R code and compile it into something called bytecode, which is basically a lower dimensional representation of the that can then be executed fairly quickly, or at least hopefully quickly. In some cases it makes a difference. In some cases that I've found it doesn't make all that much of a difference. So I'll let you look through that on your own rather than spending too much time on it right now. Okay, so I think that's all I want to say about efficiency for the moment. We'll hit on some of these topics again later on in the semester. Any questions before I move on? Okay, so I want to talk a little bit more about some things that come up when we're thinking about working with functions, and questions of copying, passing things around by value versus passing by reference, some various issues that come up. And so before I do that, I want to say a little bit about what a pointer is. And there aren't really any pointers in R, so this is really more of something that comes up in languages like C, C++, that are languages where you compile the code. But I think at least knowing what a pointer is will help us in terms of thinking about some of the topics that we're going to talk about in R. So the basic idea is that in a language like C, we can think about there being, say, a variable named x, and maybe it has the value 3 in it. Well, that value has to be stored somewhere in memory on the computer that we can then go look it up, access it, pull the value out, manipulate it, store the result somewhere else, et cetera, et cetera. That's sort of how you can think about it, what a computer does. Well, this value is stored in memory, so we can associate it. We can think of this as the value as having some address. That's the address in memory of where the number 3 is stored. And so that's usually written as some hexadecimal number, so often you'll see this as x, indicating that it's a base 16 number, and then some number like that's written in base 16. Okay. So that's what you would often, that's sort of a representation of how things are stored on the machine. And if we were working in a language like C, we can write code like this. We could define a variable x, set it to be 3, and then we can do things like this, with variables with things that are called pointers. And so I'm going to create a new variable that has this syntax that's called a pointer. So this is going to be a pointer to an integer. And I'm going to assign that pointer to be the address of the variable x. So what does it mean when I do this? Well, basically what I'm saying is there's going to be some new variable, which I'm calling ptr, and in it, after I run through those first 3 lines of code, it's going to have stored in it the address of x. So these x's are different. Let me just erase those because that's not really material here. So this variable, which is an integer pointer, just stores the address of an actual integer. And if I wanted to refer to the value 3, I could either refer to it with x, or I could do something called dereferencing, which is take the pointer, the variable that points to the value. Another way to think of this is this pointer, I can sort of think of this as being an arrow to the actual thing that I might be interested in. I can refer to the actual value 3 by dereferencing the pointer and saying star pointer times 7. So here the asterisk is being used in 2 different ways here. Okay, so that's a little bit about what a pointer is. It turns out if we think about vectors in C, we can think about storing a vector, say, of however many numbers here, 3, 7, 5, whatever. And when we think about vectors, or we call them arrays in C, basically, if this thing is x, if this whole vector is x, then an x of 0 is the first element, that's a 3. And what x is actually, really bad luck today, what x actually is it's just a pointer to the first element of the array, or the vector. So x itself would really be whatever the memory location is associated with this value 3. Maybe it's the 1e, f, whatever. So it would just have that value. And then whenever you index into a vector, So C index is starting with 0 rather than with 1. Whenever you index into a vector, it's basically knowing that the start of the vector is here, and then it knows how far to jump to get to the index value that you're interested in. Okay, so that was all a little bit roundabout, but the thing that's helpful to know is that in languages like this that have pointers, I can pass in a pointer as an argument to a function. And then if I manipulate the pointer and the values in the objects, in the variables that are pointed to by that pointer, this is going to have an effect on the variable that was passed in to this function that I'm calling mycal. So in the case up here, pointer was a pointer to that value x, and x contained 3. And if I call this function, this says, take whatever PTR points to, which was that x that has a value 3, and add it to itself. So I get 3 plus 3, that gets assigned to 6. And the result is that that x, which was 3 originally outside of this function, would now be 6 outside of the function, even though I don't actually ever see x appearing in the function here. And even though I haven't passed x back out as the return value of the function. So this mechanism of passing a pointer in, manipulating things in that, and then the result of that having an effect on the variables that are defined outside the function is called passing by reference as opposed to passing by value. Passing by value is what R does. If we did this, this is called passing by reference. Okay, so questions about that? Okay, so the reason I wanted to go into that was to say, okay, we know that in R, in general, we're passing things by value. So basically, we pass something in. If we modify it, the only effect of the modification is within the function. And if we want to then change things outside of that function, we have to pass back via return. We have to return back whatever the modified object is that we're interested in. However, there are a few ways around passing by value, and that's really what I wanted to talk about here. So first off, there's this new thing called reference classes that are fairly new within the last few years in R. When we get to section 4 of this unit, we'll talk about reference classes in combination with talking about other aspects of object-oriented programming in R. So that will be something we'll see in some detail there. Another thing that we can do is we can access an object in the enclosing environment and work with and actually assign values into the object in the enclosing environment. So I forget if I have a demonstration of this or not. Perhaps not. So basically what I can do is I can use this assignment operator that looks a little bit different than the usual assignment operator, which has 2 less thans and then a minus. So if I have some function and I do something like this in that function, that tells R to try and do this assignment in the enclosing environment. So suppose this were defined in the global environment and I had set x equals to, let me use the actual assignment operator. I had set x equals to 7 outside, and then I ran this function. The result would be that x outside would be assigned to be 3 instead of 7. So that's one way you can work in the enclosing environment and basically have the functionality of having sort of like a global variable depending on exactly what the enclosing environment is. You could also use the assign function to do this explicitly and tell it what environment to do the assignment in. So that's another possibility. So this would be one way to have an effect, have the effect of running your function have some effect outside of the actual function. We'll also see things called replacement functions, which are basically things like this, or there's a diag function for working with matrices that we saw briefly. You can do things like this, and so whenever you've got sort of basically function calls on the left-hand side of an assignment, there's some sort of funky stuff going on behind the scenes in R, and that basically sort of hides the fact that, or it sort of allows you to affect the objects. What am I trying to say here? basically it allows you to do assignment in the in the environment in the global environment. Okay, so we'll see that in a little bit as well. The other thing I want to mention is this idea of a closure. And this came up when we were talking about scoping in Unit 4. So the idea was, this is basically just more or less that same kind of function that we saw in the other unit. Suppose I define a function that itself defines another function, and then I pass that new function out of the original function. But suppose what I've done is I've taken an input so f is sort of a function constructor. Its job is to build functions and return them. And my function constructor f takes an input that I'm calling input, assigns that to be something called data, and then this new function that gets created actually uses both its input, whatever its input ends up being, its input argument, as well as this thing called data. So if I run this, I'm going to create the function by calling f, and then I'm going to remove that original x, and then I'm going to run my function. So let's actually see this here. Okay, so x, which is a random vector of 10 values, has gotten passed into f, and it's now in the enclosing environment of G. And as we saw a couple units ago, that enclosing environment gets preserved even though the function f finishes its execution. And so the object that's called data, which holds the value that those 10 random values that are in x, is now going to be associated and carried along basically with this function g, which is, or in other words, with this function myFun. So if I can now remove that object x from my global environment, and if I call myFun of 3, what it's going to do is take the value 3, which is the param, the input argument for g, and it's actually going to multiply it by that vector of 10 values, because that vector of 10 values is in the enclosing environment of myFun. It's in what's called the closure of myFun. So that's an illustration of basically associating objects with functions, so that we can basically, as a workaround to having global variables and manipulating objects outside of the function, as we sort of have this data object that we're interested in, this vector of 10 numbers associated with the function. And I won't take the time to look at this, but do take a look at this for Wednesday. Just take a few minutes and sort of puzzle through what's going on here. What you'll see in this function here is that basically it creates some objects in the closure of this new function here that doesn't have a name. It's an anonymous function, but it creates those objects x and I in the closure of this function, in the enclosing environment of this function. And then it actually assigns to x and assigns to I with this assignment operator that we just saw a few minutes ago. So this looks in the enclosing environment, sees there's an x, sees there's an I, and is able to assign into it. And this is another way, this is basically an extended example of using these closures to basically do things that are like pass by reference as opposed to pass by value. So the idea is by having x and I bound up with the function and using this particular syntax, we can basically manipulate the values of x and of I when we call this anonymous function here. So if we actually ran through and did this, we can see that we're going to make a function called bootMeans as a result of running this function constructor up here, the make container function, and then it allows us to basically act in a way that's sort of like passing things by reference. Okay. Let me talk a little bit about operators. So as we've actually already seen this a little bit, this idea that an operator is just a function. It happens to be a function that takes its arguments both on the left side of the operator and the right side, whereas usually we think of functions as just taking their arguments within parentheses. But I could equivalently execute a plus b as a plus b, or call the plus function on the arguments a and b. We've seen that we can do some slick things with, say, with sapply, where we pass an operator in as the function that's going to be sapplied to a list. And for example, that allows us to pull out particular elements, pull out a given element from a list, from each element of the list. Forget if we saw this before or not, but you can basically, the outer function is a way of doing pairwise operations on two different vectors. So usually you think of an outer product as being the, as taking all of the pairwise products of the elements of two vectors and getting a matrix out of that. But we can think of an outer operation also as just being pairwise, say, addition in this case, where I have a vector x, a vector y, and I do the pairwise additions of the elements there. And this is another example where we can pass in either a function or an operator as the function that that outer is then going to execute on the pairs of inputs. And then a couple other things that come up when we're thinking about operators is, one, if we want to define our own operator, as long as it takes two arguments, then R will allow us to do that. So I could define a sort of silly operator that I'm going to call the to operator. I put it in backticks and I give it a name. And then I just have to say, well, it's a function, and I have to say what the function does. And so I'm going to say that my to operator takes two arguments, adds them together, and multiplies by 2. So now I could use the to operator with numbers and then get back, that execution on those inputs. So that might come in handy every so often. And we've sort of already seen that this is sort of how R constructs its built-in operators. We know that matrix multiplication is percent multiply percent. Right? So R came up with an operator that stands for doing matrix multiplication, so that you don't have to type out, mat mult or matrix multiply or whatever would be the name of a matrix multiplication function. Instead, it's written as being an operator. And then the last thing I was going to say about operators is, one of the things to recognize about them is, because they're just functions, sometimes they take additional arguments that you're not aware of. So we've created a matrix here. I'm going to then do some subsetting where I pull out the first column. So that's just going to give me back a vector 1, 2. So something a little bit funny happened here that we don't usually think about, but is useful to think about sometimes, which is that we started with a matrix. Depending on what kind of subsetting we did here, in this case we ended up with a vector, but in other cases we might actually have continued to end up with a matrix. Suppose this were a 3-column matrix and I pulled out the second and third columns, the result of that would still be a matrix rather than a vector. So that's the sort of thing that if you're writing code could actually cause bugs and errors, that you write some code and depending on the size of the input matrix, you might either get a vector as a result or you might get a matrix as a result. And then if the code that then gets run later on is expecting a matrix, but it turns out it only got a vector, that a vector was created in the interim, then the code is going to fail. So one way around that is to recognize that there's actually an additional optional argument to the square bracket operator, which is this argument drop, which by default is set to true and says, okay, if I do a subset on a matrix and the result could be coerced to just be a regular vector, it could just be, in essence, it's just a vector, change it to a vector. But sometimes, as I just said, that might not be what we want. And so if I do the square bracket operators but add on this additional argument that says drop equals false, it won't drop that second dimension of the matrix, and it will retain the result being a matrix. In this case, it's still only going to be a 1-column matrix, but it's still going to be kept in R as a matrix as opposed to a vector. So that's both sort of useful as a particular example and also an illustration of this idea that operators are just functions. Sometimes they have additional arguments that we might not expect. And if you look at the help information for the operator, then you should be able to see that that's what's going on. So if I did this with the square bracket operator, you can see that it gives some usage, and then it says, hey, you know what? There is these additional arguments that maybe we weren't aware of, and those are things that we can make use of. Okay. Questions or comments at this point? Okay, so continuing on this theme of sort of functions being at the core of how R operates, we can actually basically think of any call or execution that we do in R as basically running a function behind the scenes. So if, for example, we looked at this statement, which is just an if-else conditional statement, how can we think of this as being a function call? What would the arguments to this, if we were thinking of this as a function, what are the arguments to this function? Say it again?
X.
Not quite x, a little more than that. Think about the whole set of 4 or 5 lines as a function call. Say it again about the true or false.
It's a logical vector, and whether x is larger than x.
Okay. So depending on the result of this, we either execute this or this. Right? So we can think of the first argument as actually being this conditional check that it does. So we can think of the first argument as being the condition. That's going to get evaluated and then give us a bunch of trues or falses. And then we can think of the second argument as being the body of what happens if, actually it's not going to be a bunch of trues or falses. Right, this is, hopefully, let's think of this as a scalar, because otherwise we're going to get in a little bit of trouble here. Assuming that this is a scalar, this is just going to be a true or false. So the first thing we can think of as the first argument here is just the condition that gets passed in. And then the second argument would be, what do you do if you get a true? And the third argument is the body of what do you do if you get a false from the else. So it is actually possible to write this in R basically as the if function, with the first argument being, in this case, the condition x greater than 27, the second argument being whatever the body of code is here, and the third argument being the body of code is here. And that's actually what R is doing behind the scenes. The R interpreter sees this code, it recognizes the if and says, oh, I'm running the if function, and it has 3 inputs. So it basically has to parse through this syntax, find the condition, find this body of code, and if there is an else, find this body of code. And then it dispatches a function call that basically does what I just said. It passes those three arguments in and does the operations that we would expect to occur here. Okay, so I've already said that there are also these things called replacement functions or replacement expressions. These are some examples of those. Basically, anytime you see something that looks like a function or operation on the left-hand side of an assignment. And so these things are actually also function calls. They're very special function calls, which is, again, the R interpreter, when it goes through and sees something like these things up here, it's doing a little bit of gymnastics behind the scenes. And what it's actually doing is something like this. Here I'm going to create a matrix, and I'm first going to do it with this notation of the replacement function. But what it's actually doing, another way to write this, is it's calling this function, the diag replacement function, on the matrix with whatever it wants, with whatever you want to do the replacement with. It's creating a new matrix based on having substituted in these values for the diagonal of this matrix. And then it's reassigning that to the same object name. So it's basically doing all of that behind the scenes, and we could actually see what this function looks like by actually looking in R at this, the name of this function in the base package. But the sort of tricky thing that's going on behind the scenes is basically doing this calculation, changing it's basically creating a new object, but then it's just very, sort of behind the scenes, renaming that to be whatever the name of the original object is. And so the original object exists in memory for a little while, and then it gets cleaned up by this thing called the garbage collector so that it's not taking up space in memory. We'll see a little bit about that in the next section. But the interesting thing is that this is sort of what's going on behind the scenes. So I guess let's pick up there on Wednesday. Do go ahead and look at that example of a closure that I mentioned here on page 18 for Wednesday, and we'll come back and see if there are any questions about that on Wednesday.